Okay. Uh, so it is recording. Okay. So I think yesterday I had a meeting, right? Yesterday I had another session. Sorry for some trouble with setting up the things actually. Yeah, my apologies. I think I will start the meeting session right now. So welcome to the introduction to quantum computing. Basically, I think on today's lecture we are supposed to talk about some existing quantum computer architecture, that is quantum computer hardware like superconductor, ion trap, and some the mathematical things like how we can compute mathematically, like bracket notations and some other quantum gates, actually how it works. So initially let's start with uh, the bit and qubit things actually. So basically in classical, we all uh, know that mm, all our laptop and mobile device, whatever the existing current device it is, that works on classical things, those are bits actually. Basically uh, basically those are 0, 1. Those are just the combination of 0 and 1. So basically these all are works at a single times actually. These are single. That means when you work on this particular 0 bit, they're just a particular 0 bit, we work on it, we manipulate on it, and we compute things on it. And when you work on 1 bit, we just work on 1 bit actually, the bit 1. But in case of quantum computation, the scenario is quite different. The different scenario means we don't say it bit. In case of quantum computing, we call it qubit actually. So basically, we start with the very fundamental state of qubit. We call it cat notation. The way we represent a bit state for a quantum computing or for a qubit, it is cat state. So let's say what is the cat state for 0 if we start with. So the cat 0, that means it is a column vector basically, or you can say also column matrix. So when I say column matrix, its representation is something like on here is 1 and here is 0. And when I say cat 1, basically it will be something like this. I'm writing cat 1. So in case of cat 1, it will be 0 and 1. So now we can give a look at cat 0 and cat 1 actually. It makes sense. Basically, whenever now we are going into quantum computation and how we represents matrix or qubit states and different states for a qubit actually. And here we can see that here is two row. This first row represents for classical bit 0. Represents for classical bit 0. This is a single qubit state. Actually, this is single qubit state. That's why you can say the first row represents for classical bit 0. The second row represents for classical bit 1. So what we can say for these column vector or column matrix, actually, we can say that classical bit 0 has some value and classical bit 1 does not have any value. That's why it is cat 0 state for a qubit. On the similar analogy for cat 1 state, when we say, we can, like I said, just this first row is for classical bit 0, how it is second row for classical bit 1. We can say that classical bit 0 has no components, no value, but classical bit 1, it has some values actually. So this is for single qubit. Let's say now I want to represent uh, 0, 0, cat 0 in qubits actually. So cat 0 in qubit. So how we can write it, cat 0? Sorry for some my bad handwriting. Uh, so basically, how we can write cat 0 for this actually? So I'm just writing it down, then I'm explaining. Then I will have a question to you guys. It would be great if you participate on it. So I'm just writing down the cat 0 for a column matrix or column vector. I will have 1, then 0, then 0, then 0. Uh, Now you can see that there is 4 rows actually, and these 4 rows are, this is for 0, 0, this one is for 0, 0, classical bit 0, 0, and this one is for 0, 1, classical bit 0, 1. The same analogy, this is for 1, 0 classical bit, and the final one is for classical bit 1, 1. Now you can see that here is the beauty of quantum actually. If we compare this one, if we compare this one and this one, we can see that in a single matrix, we can compute or we can deal with 4 for a 2 qubit, for a 4 classical bit state, and for a 1 qubit for a 2 classical bit state. So basically, in that case, we can say that quantum computing works on a superposition things actually. This is the superposition things. The superposition things, and another way of explaining superposition is something like all the qubit states are uh, placed or can be replaced at the same time actually, simultaneously. This kind of things, you can see that there are 4 classical states for a 2 qubit, there are 2 classical bits for single qubit, and I can make a column matrix for all of them at the same time actually, and I can manipulate all of them at the same time. So the question to you guys, if I want to write 1, 0, cat 1, 0, how should I write it? Uh, Please participate. Any response? Does it make sense what I said? If I want to write 1, 0, then what will be the column matrix for this? You can tell me, I will write down actually. So uh, I'm not sure. Am I audible or just give me a second?
Sir, I think it'd be 0010.
Uh, yeah, that's perfect actually. Thank you. This should be 0, 0, and 10 actually. Yeah. So now you can see that mm, this is 0, 0. This is for 2 qubit 0, 0. Then what will be for, you can also write 0, 1. Then we can write for 1, 0. Then we can for write for 1, 1. And the way of number of qubit or class bit, uh, the number of bit increase, the number of column, I mean the number of row also increases with 2 to the power n. N means qubit, the number of qubit. In this case, we have 2 qubit. Here is 2 qubit, and here we have only 1 qubit actually. So we can say that for 1 qubit, 2 to the power 1 is 2, 2 to the power 2 square is 4 actually. So that is yeah, 4 qubit. Yeah, 4 qubit stress representation in here actually. So basically, this is for cat notation. Now we can describe what is for bra notation actually. Basically, I'm just here explaining the real number examples actually. The in cat notation, let's say a generic explanation of cat notation could be, let's say for x, this is a qubit state of x. Typically, don't write x. It could be a actually for matrix a, and it can be a complex number actually. So something like a plus a00, a00, a0, it could be equal to some complex number, let's say alpha plus I beta actually, and it goes on. uh, so yeah, so what I'm trying to make a point that uh, cat notation or bra notation, whatever it is, those all are basically complex actually. And quantum computing mainly deal with also complex numbers actually. In classical, mainly we deal with real numbers actually, and that's where two come from actually, if we can say, because complex number has two components. There is a real component and there is imaginary components, and then we can say this is on Hilbert space actually, because Hilbert space deals with complex. This is a complex plane actually. So there is two components, and these two also come from, if we say for Hilbert space calculations, then these two also come from this complex, two part of complex, real number and imaginary part actually of complex number. So here is the cat notations actually. So let's say we want to write a brand notation for this cat 0 actually. So the brand notation will looks like this, just opposite. This is a left triangle, this is called angle. So the left angle, what it happens, we will swap column and row. We will swap column and row. So that means the elements of column will go to row and elements of row will go to column actually. So it will looks like 1 and 0 in this case. That means basically there, as this is a single column, we'll just swap it actually. As this is real number, so we have no worry about it. But if it was a conjugate number, then we have some worry. Let's say I'm sharing another step. This is I actually. Uh, I will explain. This is a very important step actually. This is one of the basis step that for quantum computation we deal with. I will explain what is basis states in later, but let me just describe cat and Brown notations actually. Uh, what are the basis states? This I is one of the basis states for quantum computations. So the basis states of I is looks like this is 1 over square root over 2, 1 over square root over 2, and this is for 0. So that means classical bit 0 has value 1 over square root over 2. But for classical bit 1, the value is I. This one is imaginary, then 1 over square root over 2. We can make a common for 1 over square root over 2, and in that case it will look like 1 over square root over 2. Then classical bit will have 1, then there will be only I, imaginary number actually. So now if we want to make a Brown notation for this, how it will look like? Basically Brown notation of I will look like, we will make this column vector into a row vector. So this will be 1 over square root over 2, then I, there should be I, this is imaginary, then 1 over square root over 2. And finally I said we have to make a complex conjugate. So complex conjugate of, there is only I, this is a complex, I have to make a conjugate that it should be minus I actually. So now the question to you, in here I said I will make a transpose, like swapping row and column, this is called transpose, and I will make a conjugate actually. So I'm doing transpose first, then making conjugate, and that's how I'm getting bracket. So what if I do the reverse things actually, the other way? Other way means I will make the conjugate first and make the transpose later. Will it make any difference? uh, I have a question to audience. So basically the way I describe, we can write Brown notation is, at first we made a transpose, then we make a complex conjugate. But if we want to make a conjugate first and then make a transpose, will it make any difference? uh, yeah, 30 seconds thought. Please respond. Hmm? Well, I think it could be a homework actually. Just proof. Uh, it could be abstract more. The proof is something like, let's say I have a matrix. This is a homework. I think I'm giving him a homework. So the homework is, let's say I have a matrix. Okay, I have a matrix. So if I make a transpose of it first and then make a conjugate, the order, this is the order. I make a transpose first, then conjugate it. And the question is, if this order is equivalent to conjugating first a matrix, then uh, making a transpose actually. So you can prove it abstractly or you can prove it with numerics actually, whatever you wish. But I think abstract proof is quite good in that case. The more you will deal with linear algebra or matrices, the more you will understand how qubit states are changing actually. Although we mainly uh, people who use are, yeah, although mainly people just do coding actually, but to get the overall visualization things, I think in initial stage these things should be feel it actually, or these things should be realized, that how the matrix formation is going on actually. Okay, so like I said, this is for Brown notation of 0, and like if you I want to make a Brown notation for 1, so what it should be actually. So I will just uh, okay, I'll just make this column vector into a row vector. So it will be 0 and 1. It will be 0 and 1 actually. So we will do a lot of yeah, basically this is a cat and brand notation actually. So but now we will deal with how we can make a product of these cat and brand notations actually, because these things are important. There are two kind of products. One is called inner product and one is called other products actually. So okay, uh, one is called inner product and one is called other product. So let's say for I'm showing a inner product between cat 0, sorry, this is bra 0. This is inner product. This is inner product. Inner product means bra notation will be first, then there will be cat notation. This is called bracket. This is called bracket. Like this is for bra. This 0 is in bra state. This 0 is in bra state, and this cat is for 1. Cat is for 1 state actually. So there's two vertical line actually. So we can make it 1 actually. So this is for bracket notation. Now if you want to um, write the bracket notation for these, we know bracket notation for 0 is 1 and 0, and cat notation for is 1 is 0 and 1. Now we'll do just a simple matrix product. So how the matrix products looks like. The matrix products, it is 1 multiplied by 0, 0 multiplied by 1. This is 0. So the inner product of cat, sorry, bra 0 and cat 1 is 0 actually. So if we make inner product between bra 0 and cat 1, it will be get 0. Now question is, what does it mean? Basically, it means that when we say bra, bra 0 actually, it is a basically these two strings are orthogonal actually. Whenever say orthogonal, we can say basically this is for 0 and this is for 1. The projection between 0 and 1 is 0. How we can say, how we can feel that projection between 1 is 0? So basically, if we can say 1 and 0, let's say there is a sun above of all of them. There is a sun above of all of them. Sun is lighting this 0 and 1 plane. So now the question is, how much shade we will get for 1 over 0 actually? How much shade we will get for 1 over 0? If as this is vertical, so you see there is no shade for this. It will just yeah, things. But if there is a projection is something like this, then we might get some value actually, because there will be shade for this length. This is the length we'll get shade and we'll get value. Why this is important? Basically, this is important for uh, measure the qubit states. Like for classical bit, basically the way our laptops or our mobile devices are works, basically these are the voltage level actually. When I'm not sure how many of are in from electrical engineering, but we send in electrical engineering circuits, you'll find that uh, we send some rectangular wave pulse actually. Basically, this looks like this. When I say rectangular wave pulse, they look like them actually. This kind of wave pulse to the circuit actually, and there is a 5 volt actually. There is a 5 volt and there is a 0 volt actually. So the 5 volt means 1 and 0 volt means 0 actually. So uh, yeah, so the for the classical bit distance actually, these are the just 1 and 0 combination. That's how our computations works. All the laptop, all the mobile device, all the current technology is based on just these voltage levels actually, 0, 5 and 0. I mean the yeah, the microelectronics things actually. So we just check the voltage level actually, and there is some threshold. If we say the voltage level is more than 3, then we can say we just measure the voltage. And if we say, if we find that this is more than 3, then we can say this is, yeah, this is 1 for classical bit. And if it's less than 3, then we can say, yeah, this is 0 actually. But for qubit states, the way we want to measure of the bit states or things, I mean the qubit states actually, this is probability actually. And probability is something like projection. At this moment, there is a lot of some jargon things. I'm not going into there, just to describe. Basically, these are the projections, and projection depends on the basis states actually. In this case, our basis states is 0 and 1. This case, our basis states is 0, 1. I will show you in just a few more minutes later. Uh, yeah, after end of these products part actually, we are dealing with inner product. There will be outer product, and after that, in later part of the session, I will show you that depending on the basis sets or basis states, these inner product value get changed actually. So our probability, the way we are going to measure qubit stress, this is totally dependent on our basis stress actually. I mean basis sets actually. And there in quantum computer there are some other there are infinite number of basis sets mathematically. There are infinite number of basis sets actually. But for initial case, I think mostly two are the most important one that mostly people deal with. 0, 1 is one of them here, and another is oh sorry, it should be second parenthesis. This is plus, this is minus, plus minus basis sets, and another one is uh, plus I minus I. This is plus I and this is minus I. Plus I and minus I. These are the two basis sets actually. So yeah, I will explain a bit later that what is the cat state for plus and what is the cat state for minus. And I think I already described the cat state for plus I, and cat state for minus I will also discuss actually. But Yeah, for this moment, the orthogonal, when two basis states are orthogonal, they all are orthogonal to each other. Plus and minus are orthogonal to each other. Plus I minus I are also orthogonal to each other. 0, 1 is also orthogonal to each other actually. So that's why when we make an inner product between two orthogonal states, we'll find 0. But if we make orthogonal between on it, let's say this is 0 and there is a sun, and we want to make projection over it actually. So what will happen? I will get the full shade over it. Full shade over it. That means I will get the whole value. That is one. So we can check it. Let's say there is cat1, and sorry, there is bra1 and cat1. So how the value will looks like? It will looks like 0 for bra1, I mean for this bra1, 0, 1, and for this cat1, it will look like uh, column vector 0, 1. Now do the matrix product, you will find 0, 0, 1, 1. Oh, I'm sorry. You will find 0. We'll find just the value 1. Sorry, apologies. We'll find the value just the 1. You can do the matrix products. 0 multiplied by 0 is 0, 1 multiplied by 1 is 1 actually. So that's it actually. So do you have any questions so far? If you have any question, please feel free. Part of that, charge my laptop. This is good. Okay. Um. So far we studied inner product actually. So now we will go to outer product actually. So outer product is inner products is called bracket. So the outer product will be obviously cat bra actually, the opposite way. So let's say the cat bra notation. This is for 0 cat, and this is for we can talk about 1. Uh yeah, cat this is cat 0 and this is bra 1. So what will be the matrix for cat 0? The matrix for cat 0 is for 1 and then 0, and the matrix for bra 1 is 0 and 1. Can you do the matrix multiplication for this? uh Someone please do the matrix multiplication and tell me what will be the matrix multiplication for this. Anyone? No, I'm not sure if it is going very easy or very hard actually. Please guys respond. Otherwise, I'm not be sure how it is going actually. Uh, if I okay, I will write it down actually. In this case, you cannot do normal matrix multiplication for this because there is some condition. There is a condition for matrix multiplication. The condition for matrix multiplication is the mm, you cannot do matrix multiplication for this actually uh, because the condition for matrix multiplication is column number and row number should be same actually, but this is not this case actually. There is one column uh, and one row. Um, I think it should be the reverse way actually, but whatever. But it shouldn't be. You cannot do normal matrix multiplication for this actually. So in that case, whatever you should do, the thing you should do is uh, you have to multiply 1 by this for whole row actually. So for the 1, if I multiply by this whole row, it should be 0 and 1. I will do the same thing for this one. I will multiply the whole row by this 0. So I will get 0 and 0. So yeah, this is for 0 1 outer product actually. And this outer product is important for 2-qubit gate. I will explain how it makes sense for a CNOT gate just a bit later. So let's say this is for 0, this is 0. I will write the outer product for 0 and 0 actually. So how it will look, the outer product for 0 and 0 looks like uh, this is cat 0, right? So it should be 1 and 0. It should be 1 and 0. And bracketed for this, it looks like 1 and 0. This is 1 and this is 0 actually. So if we make the matrix outer product multiplication for the same process, we will multiply this one by this full row, by this full row. So it should be 1 multiplied by 1 is 1, or is 0, it should be 0. And I will multiply this full row, whole row, by this 0. So it should be 0 and 0. Do you guys see any pattern actually? The pattern is when there is the outer product by 0 0, I found that the yeah, top left corner, the top left corner is getting 1. For 0 1, the top right corner is getting 1. Now what will be the case for 1 0? No, it should be, yeah, uh, it should be cat bar notation. I have written bracket notation. It should be cat bar notation. So cat 1 and bra 0. If you do the matrix multiplication, you see the pattern actually from these two. You see the pattern actually, like I mentioned, 0 0 top left corner, 0 1 top right corner actually. So what will be the case for 1 0? The case for 1 0 will be uh, 0 0. There will be only 1 in here. There will be rest of the things will be 0. Do you feel it that why the bottom left corner is 1? You can say that because the cat 1, that means cat 1, the 1 has in the lower side actually. For cat 1, this is cat 1, this is cat 1, This is cat 1. And what will be the case for bra0? The case for bra0 will be first element of the matrix will be 1, rest of the 0. So when I make a outer product for this, I multiply this whole cat 0 by 0, first element of uh cat 1. Then I get 0 for all of this. I got this row, because if you multiply 0 by this whole row, you will get 0 0. But if you multiply this whole row by 1, you will get 1 and 0 actually. I think now we can write 1 1. So it is easily can be said that there will be only 1 in here actually for cat brand notation, or for outer product. All will be 0. All will be 0, but this will be only 1. So it's a cool thing actually for 2 qubit gates actually. How it is cool qubit? Uh, if we make summation all of this, if we make summation of all of this 0 0 will start from 0 0, will start from this 0 0, then 0 1, then 0 1, then 1 0, then 1 1. What we will get actually? We can see that for 0 0 there is 1 0, there is only 1. For 0 1 there is 1 on the top right corner, there is 1 0 for the bottom left corner, 1 1 for the bottom right corner. So if we make a summation of all of these actually, so what we'll get, we'll get 1 1 1 1. How it is important? It is important for making a C not gate actually. C not gate. This is a controlled not gate actually. This is a controller. Now we are getting into gate actually. Now we are getting into gate. This is control not gate. This is one of the most fundamental gate for fundamental, most used gates for quantum uh, computing people actually who does quantum computer. This is for CNOT gates actually, and CNOT gate is important. Basically, how good a quantum architecture, be it superconductor uh, mm, based quantum computer, or ion trap based quantum computer, or any other Majorana based quantum computer, whatever it is, the architecture it is. Uh, uh, CNOT gate is mostly used, and CNOT gate is the parameter, especially for CNOT gate, how the architecture it is. You will see that uh, if we check IBM Quantum lab website, and you will find that there are some device name actually, and you will see find CNOT error. There is a specific term for CNOT error, because 2 qubit gates are mostly error prone for quantum computer actually. And how much error prone actually? Let me share an analogy for this actually. Basically, our existing classical computer, laptop, mobile device hardly makes error actually. There is a billionth of 1 in a billion's operation. There is a probability uh, it will make an error. That means if I make a simple circuit and run it for 1 billion time, it will get error results. It will give me error results for only one time actually. But for case of quantum computer, if so far the current state of the art says that if I make a quantum circuit and run it for maybe thousands times, I will get at most 30 times correct value. The rest of the times are totally error actually. For 1,000 runs, I get 30 times correct value. This is for quantum, but for classical, if I run for billion times, I get 100 billion times. If I run a circuit, I get only one error actually. That's how classical is dominating. But quantum people are trying to make progress, and the parameter for progress is how uh, less error we can make for a CNOT gate actually. How good CNOT gate can be made actually. So basically CNOT gate, that's why is quite important actually. So yeah, so the CNOT gate, how it works. Uh, Let me share some our other facts actually. Uh, if anyone is from her electrical actually, I think, do you know the number of universal gates for classical actually? I'm not sure what is the from what stage in you are for your bachelor's or master's. I don't know actually if it is for senior or junior. I think it should be taught in microelectronics that the universal gates for classical for any kind of classical gates are NAND and NOR gate actually. For classical, there are some other gates like AND gate, OR gate, NOT gate. You can make all of these AND or NOT gate through a NAND gate and NOR gate actually. So NAND gate and NOR gate are universal. In case of quantum, uh, yeah, these um, fundamental gates are basically T gate or S gate, but people don't mostly use. People mostly use C NOT gate for 2 qubit, and for single qubit people use edge gate and poly gates actually. I will show edge gates and poly gates, but for a moment let's go for CNOT gates. Before CNOT gate, let's go for a quantum NOT gate actually. We all know classical NOT gate is something like in microelectronics it is something like uh, this is the look for classical NOT gate actually. What it is does, if there is a input 0, it will give me output 1, and if there is output sorry, input 1, there will be output 0 actually. So this is for classical actually. So from there we can make matrix for quantum NOT gate actually. And for quantum NOT gate it is called poly-X gate. This is called poly-X gate. So what we got from NOT gate, the condition for NOT gate is when there is 0, output will be 1. When there is qubit state 1, output will be 0 actually. So let's say my input is 0. What should I get? I should get output 1. And what is the output 1 for qubit state 1? I mean, what is the matrix for qubit state 1? It looks like first element should be 0, the second element should be 1. Okay, now say I have input for 1. What should be the output for quantum? I mean, quantum NOT gate. The quantum NOT gate is called poly-X gate actually. This is equivalent to uh, classical NOT gate. Poly-X gate equal to classical NOT gate actually. What is this poly-X gate? If the input is CAD 1, I will get output CAD 0. So how does CAD 0 looks? It is 1 and it is 0. So the poly matrix looks like, I mean, poly X gate or sigma X gate. You will find it tons of articles that this is poly X gates, and poly X gates looks like, the matrix for poly X gates looks like this actually. And how it come from, this is came from here actually. Okay, this is not gate, poly X gate. This is sigma X gate actually. This is poly X gate or sigma X gate, whatever you call, both are correct. And now I want to make a C not gate. So for C not gate, this is a 2 qubit gate. So I need 2 qubit. The condition for C not gate is when the input uh, C not gate, the full meaning of C, that is controlled not gate. So there is some control things actually for not gate actually. What it is control? This is for first qubit. In here you can see, if I consider this one is first and this one is second, this one is first and this one is second. If first qubit is 1, then the second qubit, uh, then I can apply not gate for the second qubit. Let me repeat. If the first qubit is 1, then I can apply not gate for the second qubit. So I cannot apply not gate for this 0 1 because first qubit is 0. So there is no meaning to apply for 0 1. For this state, I also cannot apply C not gate because first qubit is 0, and that will be 0. But I can apply here because first qubit is 1, and I can apply not gate for the second qubit. And not gate for the second qubit will be 0 will be 1 actually. So the output, if I apply not gate for 1 0 cat state, the output I will get 1 first qubit will be as like as it, but the second qubit will be not get 0 will get 1. Okay, and for this case, uh, first qubit will be 1 because like I said, for control not gate, 1, if there is the 1, then I can apply not gate for the second qubit. So if input is 1 1, then 1 first qubit state won't change, but the second qubit state will get changed. It will get 1 0. So how does the output will be look like actually? So for CNOT gate, we will do the same thing for poly X gate. What are the inputs? On top, we'll write input. What are the input? Input is 0 0. For 0 0, we can say that output will also be 0 0. And what are the matrix for 0 0? It is 1 0 0 0. Then if it is input, if the input is 0 1 actually, if the input is 0 1, what it will look like actually, we'll see that the output, okay, I think it should be set something like this actually. I just made a simple mistakes to write down the matrix. The thing it is, okay, let me erase it actually, just give me a second. Let me erase these things. Make me space. Okay, now I will write. So I will write matrix for C not gate actually. Okay, so matrix for C not gate. C not gate. So the input should be 0 0. This is input 0 0 0 1 1 0. This is input 0 0 1 0, and this is 1 1. This is input. And when the input is 0 0, if I apply C not gate for 0 0, I will get also 0 0. When I will apply 0 1, I will also get 0 1. When I will apply 1 0, I will get 1 1. When I will apply 1 1, I will get 1 0. Do you see I have written down 1 1 letter and 1 0 because this is for order. I mean the order of how we will expand the bit actually 0 0 0 1 1 0 1 1. This is the order. So when the input is 0 0, output is 0 0. So I will write 1 in here. So all of the rest things are, if the input is 0 1, there is no way to get 0 0 output. If the input is 1 0, there is no way to get output 0 0. So that's why I'm writing 0 in here, in here. Now if the input is 0 0, there is no way to get output 0 1. So here I will also write 0. If the input is 0 1, there is the output for C not gate will be 1, will be also 0 1. So that's why I will write 1 in here. And for 1 0 input, there is no way to get 0 1. So I will write 0 in here. For the same thing, I will do the same thing. Now if the input is 0 0, there is no way to get 1 0 output. So I will write it 0. For the 0 1 input, I will write it 0. If the input is 1 0, I will not, I will get output 1 1. So I will write 1 in here because I'm not getting 1 0 for input 1 0. That's why it will be 0. And if the input is 1 1, if the input is 1 1, I'm getting output 1 0. You see, input is 1 1, I'm getting output 1 0. So as I'm getting output in here, I will write 1, and all the rest of the things are 0. So yeah, basically this is very important things actually. When I started quantum computing almost for 2.5 years earlier, and I first see this matrix, I have, yeah, I was very much clueless how people made this matrix actually. And when I find a way, do some, that's why I say doing hand calculation for matrix is quite important. You'll get the idea. You can do codings, you can just jump into the quantum computing whenever you wish actually. But to visualize how the whole circuits or a larger algorithm is running behind the scene, initial stage, doing this kind of uh, breaking down things like this is very important. In that case, in that case, you'll get some feelings that yeah, that's how metrics are going on, and that's how qubit states are getting changed. Actually, we can make the same analogy for poly X, because if the input is 0, this is for I mean this is for 0 1 input, this is for input 0, this is for input 1, and this is for output 0, this is for output 1. If the input is 0 for a poly X gate, I will never get output 0, but I will get output 1. That's why I've written 1. For poly, yeah, for the input 1, I will get output 0. That's why I've written 1 in here. And I will not get output 1 for input 1. That's why I've written down 0 actually. So do you have any questions so far? Uh-huh.
So the C0 gate that we are doing here, we are basically running it on two different qubit wires, right? And it's like not running on one wire.
Yeah, basically we are dealing with two qubits actually, and circuit abstract representation for this, it looks like something like this. So basically this is for the first qubit, this is the second qubit, and you will see for typically people, yeah, there is a, yeah, there should be a plus in this block. Yeah, this is working on 2 wire. Good question. Any other? I mean, I'm not sure. Just for getting the idea, uh, uh, is this the first exposure for quantum, or are you guys exposed to quantum before that? Okay. Uh, I don't know if it makes sense. Basically, I'm just trying to get the idea. If this is the first time you are learning quantum computing, I mean, is, yeah.
Done some reading before, sir. Gone through the Qiskit resources on the textbook, and
Okay. Okay, that's good. So you have some exposure. That's cool. Mhm. So this is for CNOT gate, and so far we did poly S gate. Now I will ask you to write the matrix for uh, poly Z gate actually. The poly Z gate, uh, right? This is, it looks like this. So this is poly Z gate. I will telling you the condition, how the policy get works actually, but you have to tell me the matrix. Like, you have to tell me the matrix like this. Like mhm, like this actually, like sigma x. Like sigma x, you have to tell me the matrix. So the condition for sigma z is when there is zero, output is also zero. But when there is input one, when there is input one, the output will also be one, but a negative one. The condition I am repeating, if I apply zero against, I mean, if I apply zero for sigma z gate, the output I will get also zero. For sigma z, input zero, output zero. But if input is 1, I will get output negative 1. Then how the matrix will look like? Can you please someone tell me?
So can you repeat the conditions?
Yeah, the condition is, let's say this is my sigma z. Yeah, I should not use color blind color. Okay. This is sigma z. So if input is 0, I will get output 0. And if input is 1, I will get output negative 1. So write the matrix for this condition. So how the matrix will look like.
so 100 minus 1.
So it will look like 100 minus 1. Anyone wants to challenge it, or do you agree with Aditya? Aditya, okay, if I pronounce his name correctly. Okay, so anyone wants to challenge? Do you guys think it is correct? Okay, I'm moving. Basically, yeah, this one is correct actually. The reason behind this correctness is, like I mentioned, the input should be 0, uh, 0, 1, and this is for output 0, 1. For 0, I will get output to 0, so there is 1. For 0, I will never get output 1, for that one is 0. For input 1, I will get output 0, and for input 1 I will get output -1 actually. So basically sigma g is for phase changing actually. Basically uh, the reason we apply sigma z, this is another poly important poly I mean important quantum computer gate actually, quantum computing gate. uh, we sometimes have to change phase actually. Do you have guys any idea why you need to deal with phase and from where the phase comes for qubits or quantum gates actually? Uh, Let me repeat the question. Uh, why we have to bother about phase actually, and from where the phase comes for quantum computing? For quantum computing, any idea? Just a wild guess. I know this is uh, don't get embarrassed, but just share actually whatever you thought actually. Why do you think we have to deal with phase for qubit and
For like
qubit phase?
superpositioning.
Any other?
Sir, when you visualize in a block sphere, you can the state of one qubit or multiple qubits together, you can define by the phase along the z-axis.
Mm, okay. Any other?
So when you have, say, a phase gate or something, you're swinging the superposition or a single qubit, depending on which gate you're using, by certain angles, either say
Mhm.
90 degrees or some angle that you use as e power a pi by 4, or how many whatever angle you want, you can set that to swing the superposition.
Yeah, I think it is some kind of, yeah, close idea actually. Yeah, basically the I think I mentioned when I was starting the session actually, I said that uh, quantum computer are all things are Hilbert space actually. All the classical things are on real space, but quantum computers are on Hilbert space. Hilbert space means this is a complex. There is a complex. All the mathematics are complex number. So for the complex number, let's say this is a complex. Uh, there is a complex number. It is C actually, complex C. Sorry for my bad handwriting. This is A plus IB. So this is A plus IB. So to represent a complex number, you need only two things. One is its amplitude, and another thing is its phase actually. Phase means how angle it is. Let's say if I want to say 3 plus 2i, this is my complex number. This is my complex number, 3 plus 2i. So this is, if this is my complex number, so how I can represent this actually? So basically, typically what we say actually, uh, as this is 3, so for horizontally it will get 3, for vertically it will get 2. But this is real space. This is real space. But for complex, you will tell these things, and this is, if this is 3, if this is 3, if this is 2, we'll apply Pythagoras, and it will look like square root over you know uh, 3 square plus 2 square, then square root over 13, 3 square, and square root of 2 square. It will be square root over 13. uh, it will be square root over 13. So this complex number amplitude is square root over 13. and it has an angle. It has an angle. This is the angle we are talking about. This is the phase we are talking about actually. So for qubit space, the ideal representation of qubit space is, let's say I have a qubit space psi. I have a qubit space psi. So it will be cos theta by 2. It will be cos theta by 2. Then there will be cat 0. Then plus exponential of I phi, then sine theta by 2. And there we get this to 1 actually. This phi is the phase actually, and this theta is angle. This is for Bloch sphere actually, like Aditya mentioned actually. This is for Bloch sphere. So for a Bloch sphere, how it is getting rotations actually. So for mentioning a thing in a sphere, so Bloch sphere looks like this. This is not a correct sphere. Sorry, my drawing is so bad. But for mentioning a point in a sphere, I need three things actually: the radius, the angle from xy plane, and the angle from yeah, it should be phi. I should write it phi. Angle from xy plane and angle from z axis. So angle from xy plane and angle from z axis actually. So I need to, if I want to locate a point in a sphere, I need these three things actually: the radius from the center, how much I should go from the xy plane, how much I should make an angle, and from the z-axis, how much angle I should make actually. Then I can go a point through a sphere on the surface of a sphere actually. So yeah, for that reason we use phase actually, because we have to change the rotation, so we have to change the angles actually. So yeah, that is for poly Z. And if I want to apply, uh, I have written, we have shown poly X, C naught, poly Z. The only poly matrix is, I have not written down, that is poly Y. I am just writing down the matrix for this. It's your job to fill it. You will feel it how the input and how the output looks like and where it comes from. Because it's a bit tricky, because there is a complex number I actually. It, it is also for complex. So this is matrix for poly Y actually. So yeah, that's the thing. Okay, so far you, do you have guys any questions? An important homework, I think it could be, from where this theta by 2 come from. Why we have to write theta by 2 to represent a qubit state?
So I have one doubt, sir. Like most of the time, we are using this bracket notation to represent probability, right? Like the cos theta by 2 and the I sine theta by 2. Like we use it to represent probability because, like we said, the 0 means there's no chance of that output, and 1 means 100% chance of that output. But then what does here negative probability mean? Like in
uh,
sine
I
theta
think
by 2.
uh, I think in quantum computer we don't deal with negative probability. The probability has just absolute value actually, because when we measure it must be collapse actually. I think like here I mentioned actually, when we project over a particular state, over sorry not state, for over a particular basis sets actually, it must be projected on this particular basis sets. Let me share an example. This is a good questions. I have just forgotten, but yeah, it reminded
So
me.
like I'll like kind of explain what exactly I'm having an issue with. So for example, you mentioned the poly Z gate, right?
Yeah.
So if the input is 0, the output becomes 0. If the input is 1, you get the output as -1.
Mhm.
So here the only thing we are doing is we are inverting the sign.
Yeah. I mean,
But
we are
then
tracking, yeah, at 180 phase. Yeah.
but
Mhm.
we are on but then again all the gates we are dealing with, they mostly have like absolute values in the end. So what does this negative sign actually represent? Like I still didn't understand. Like
Oh,
if in the end
negative
it all
sign
becomes
is
absolute.
there is 180 phase actually from the input actually. There is 180 phase. So let's say it is more visible in sphere actually. So the phase is basically this part phi, how it is make an angle with uh, xy plane actually. So let's say if I say negative sign means it is 180 phase actually. So that's the meaning only for negative. When in quantum computing you will find I something I, you can say that the phase is right now is 90-degree, because I is the phase for I is 90-degree. So the point I'm trying to make, I mean the question you ask, it is to visualize how, if input is 1, then how can I visualize that that is -1. So basically 1 is in 180 phase actually. So in sphere, let's say uh, this is vertical one actually. So it is not that much visible, but let's say uh, there is an angle. I'm not sure if my hand is visible from the camera actually, but yeah, let's say there is an angle, and over my angle, I'm over my hand, there is a sphere actually. There is a ball, tennis ball or basketball, whatever you can say actually. So to go this point, the tip of my finger, this is the center. If this is what I will do, I will go to straight R. If this is XY plane, I will make an angle. This is phi. Yeah, this is phi. This is phi, and from Z axis, I will go this down. What I'm doing, I'm repeating. From center, from this tip, I have an angle, something like this actually. Yeah, I'm planning to come this point, tip of my finger. So what I have to do, this is my center. This is my center. I will come R. I will make a angle for XY plane. Then I will go down, and that means I will make an angle. If this is Z axis, I will make an angle with Z axis. If this is 180 phase means it will get rotated like this. From there, it will go to like this actually. So how I will come actually? So what I have to do, this is the center. My R is not getting changed, but before that I was getting this angle, but I am getting this angle. My Z also not getting changed actually. Only thing I'm getting changed is my phi. Phi means this side, this one actually. I'm not sure it does make sense. Does it make sense what I said?
Yes, sir, it makes sense. So it's only for like the inner calculations, and it doesn't like matter in the final collapsing output.
Yeah, phase does not. Yeah, phase sometimes make an issue actually. Yeah, phase and with issue. Like said, if you collapse this one, let's say this is my basis sets. What is projection? Basically, whenever I want to measure, I make a projections. So let's say there is a sunlight in here. There is a sun. How the shade will happen over this axis? I will get shade for this. But if the angle is something like this, if there is a sun, I might not get the same shade, sun shade for this one actually. So the my measurement value will get changed actually. Yeah, for the phase it will also get changed. But typically we do it with absolute value. So mostly it doesn't get changed for the minimal calculation we do actually, but it get changed. Does it make sense?
Yes, sir, yes, sir.
Okay, great. Hmm? Okay, the thing I wanted to mention, how based on the projection, the basis sets, the probability value get changed. But before that, I have to say how we can calculate probability. Basically, the probability is calculated based on bond rule. The bond rule, this is a famous scientist, German scientist. It is named after him. He is Max Born. So what does the bond rule say? Bond rule say to make a, let's say I have a state psi, it is it is important to mention that all state must be normalized. Normalized means probability should be one. Summation of probability of all states should be one. So I'm writing like this actually. What it is saying. Let me write down it fast. I'm writing 1 over square root over 2, then cat 0 plus 1 over square root over 2. Then I'm writing it cat 1 actually. Okay. So, okay. So this is my state actually. Now, if I want to measure the if you want to make, if you want to calculate the probability of zero, actually, if you want to calculate the probability of zero, the rule is something. Bond rule says I have to make inner product of zero and the state. Then I have to take the absolute value of this inner product. That's why I said probability always. I mean, when we in quantum, there is no negative probability because there is absolute. We make it absolute. Then I have t square it actually. So make of inner product between 0 and the state psi actually. So okay. So this is my Bra notation for 0. So this is absolute. This is my Bra notation of 0. Then my psi, I will write down the psi once again. It should be 1 over square root over 2, 1 over square root over 2. This is cat 0, and this is cat 0, plus 1 over square root over 2, 1 over square root over 2, cat 1. Then I'm writing down the absolute, then whole square actually. So for a current moment, I think we can ignore this 1 over square root over 2. Then what, I'm just removing 1 over square root over 2. This 1 over square root over 2, I'm removing them. I'm removing this 1 over square root over 2. Then I have to, then there is a parenthesis for this. So this is cat 0. Sorry, this is bra 0. This is cat 0. This is cat 1 actually. And there is 1 over square root over 2. This is common. This is common for everything. There is 1 over square root over 2. So like I said, 0 and 1 is orthogonal actually. So 0 and 0, it is 1 actually. 0 and 0, if I make inner product between like set 0 0 and 1 1, I will get 1. So I will only get this value. But for 0 and 1, I will get 0 actually, because these are orthogonal. So what I am getting, only I am getting 1 over square root over 2 for a one time, because the rest things are 0. Then modulus of 1 over square root over 2, because this is real number, this is 1 over square root over 2, then I have to make it square. So whenever I make it square, I will get half. So what does it mean? It means that if it should be half. It means that for this state, probability of getting state 0 is half. Probability of getting 0 is state half. And probability of getting 1, it is your homework or you thought. You can think that if I follow this way, what will be the probability of getting 1 actually. Now, it is a question to you. Let's say I have a state like this. My state is like this. My state is okay, 1 over square root over 3. 1 over square root over 3. Then 0 plus 2 over square root over 3. This is 2 over square root over 3. It is square root over 3. Then it is 1. Then what will be the probability of, just make this calculation. I am then explaining the physical meaning of this actually. What does it mean? This is plus, I mean bra plus, and this is cat shy. Bra plus and cat shy. I'm not sure if I have shown you the state for plus, but cat shy looks like this. Cat shy looks like this. Cat shy is 1 over square root over 2. 1 over square root over 2. This one is 0 plus this one is 1. That means before 1 and 0, there is square root over 2. So I am just asking you to make this calculation. If the cat is bra plus is this and cat shy is this, what will be the calculation? Yeah, I think I can give you 1.5 minutes. Just, yeah, you can do some hand calculation and show me. Mhm.
Sir, is the inner product squared? You want the
uh
modulus
you
squared?
mean this one? Yeah,
Yeah.
this one is square. Yeah, this one is square.
Yeah. So is it 5 by 6, sir?
5 by 6.
Yes, sir.
Okay, I think we can check if this is the correct one. So what we have to do, basically we have to do, uh, this is in cat state, so we'll just write it in bra state actually. So this one is easy because this is in real number, so I will just, instead of this cat, I will just write bra for bra plus actually. Bra 0, bra 1. Okay, so this one is yeah, this one is from modulus. Then there will be 1 over square root over 2. This one is 1 over square root over 2. And okay, give me a second. Am I making mistakes? No. Yeah, this one is correct. So this is 0, then plus, this is 1, and then I have to make a cat notation of this. There should be 1 over square root over 3. I can write this 1 over square root over 3 in here, so that all the unnecessary things come out in here. Sorry for my bad handwriting. This is 0, cat 0. I'm writing this state actually. So yeah, the plus 2, then cat 1. There is a first bracket actually. So there is modulus, then there is whole square. So what is going on? So this is bra 0 and this is cat 0. So I'm only getting 1 in here. So I'm getting 1 in here for this one. I can use a different color. Sure. Okay. Uh, for these, for these, yeah, for this bra and this cat, I'm getting 0. For this bra 0, and this cat 0, I am getting 0. Oh, sorry, because yeah, because they are orthogonal. For this bra and this cat, I'm getting 1. For this bra and this cat, I'm getting 0. And this cat, this bra and this cat, I'm also getting 0. And this one, I'm getting 1. For this one and this one, I'm getting 1. So what I am getting? I'm getting only 1 in here, and for this one and this one, I'm getting 2. 1 multiplied by 2 is, it should be 2, because 2 is multiplied by everything in here actually. So what I am getting? I am getting, there is 1 over square root over 2 and 1 over square root over 3. It should be 1 over square root over 6, and there here is 1 and here is 2. That means 3. That means 3 divided by square root over 6. Then I have to make it whole square. It should be 9 by 6. How you get 5 by 6? I think, I don't know, maybe you squared it and then did some things like this. It should be 9 by 6. I think you can recheck. Should be 9 by 6. Mhm. So what does it mean by this actually? So what we did in here actually, the thing we did actually, we projected this state psi on basis state plus. We projected this state psi on basis state plus. If you do the same thing for minus, you will get another different value. You will get another different value, not 9 by 6 actually. And for minus minus state, there is only minus in here actually. For plus state there is plus, for minus state there is minus actually. So uh, yeah, if you check that, you will find that for different basis states you are getting different value actually. So yeah, so that's the point actually. For different basis states we will get different value actually. So that's why basis state is important. And basis state is, in the analogy I was giving, is the sun actually, upon which I am projecting. So sorry, not sun, not the axis actually, upon which I am projecting actually. The state I am projecting on which axis. Let's say I have a state, this one is my state, this is my x-axis, this is my y-axis. The projection of this state on x-axis is not the same for the y-axis. You see, if there is a sun in here, the shade will be this long for x-axis, and for y-axis maybe this long. This value and this value is not the same actually. So yeah, I think yeah, let me check if I have any other thing. Mm, mm, uh, where am I? Yeah, these are for Python coding, how we can write some bracket notations. These are inner products, all the things. I made some homework for you. Uh, there are also some other slides for uh, explaining some other fundamental things. Yeah, these are for how we can make entanglement using Bell state, and those are for algorithms. While you are good, you can give a look at them. Uh, and then one thing, I think this one is important. I'll share. I'm not sure how I can share actually on these slides actually. I mean, I can share the file later. It is loading. So here are the some other things actually. How quantum, basically all quantum gates show reversibility and unitary functions things actually. How we can uh, prove that quantum gates are reversible and quantum gates are unitary actually. So I have shown some examples and some codings with them actually. If you are interested, you can give a big dive in here. And also a just quick, what should I say? Yeah, a quick uh, representations of, not this window. which we do. Yep. Yeah. How the ion traps works actually. I think I can give a quick intro. How the ion trap, how we can make computation in ion trap actually, and how is the architecture for ion
Hello,
trap. Yeah. Hello.
hello, Sakib.
Hmm.
Yeah, actually, what I was conveying to you is that, like, since you have only, like, 10 minutes left, and you have covered the, like, most of the topics today. So you will be again getting a time on Saturday evening. So maybe you can teach in the 1 hour about the iron traps and other hardware. Like, it will be more better. You don't have to hurry today for like 10 minutes.
Oh, okay.
You can just
Okay.
teach,
Okay.
yeah, in a very nice manner next on 8th, Saturday 8th.
Okay. Okay. I
That
think
will be
you.
convenient
Yeah.
also for you.
Yeah. For the students, they will get a. Yeah.
Yeah,
They can give a big dive on it actually. Yeah.
absolutely.
Yeah. Then in that case, do I? Can you please someone share email address? I think you, it looks as you are the organizer. So I think
Sorry, email address of, sorry, email address for which one?
so that I can share the coding I showed you that so that they can give
Oh,
a
yeah,
look.
you can share it on a Discord. You are already on Discord, right? I mean, we
Yeah,
we
yeah.
have the, yeah. So you can upload the files there. Everyone
Okay.
will be able to access. Yeah, everyone has access to Discord, and they
Mhm.
should be able to access it there.
Also, I wanted to know what about the recordings of the sessions? How will you be sharing that?
Yeah, ma'am. So for recordings, actually, the recordings have been processed, and we will be uploading them to YouTube, and we will share you a private link on Discord. So it will be private to only VIT club members
Okay, as a YouTube link.
as a YouTube link. Absolutely.
Yeah. Okay.
Mhm. Okay, that's cool actually. So I think on Saturday this is 8. What time is it? It is same
8
time.
p.m. to 9
Oh,
IST. 8 p.m. to 9. 1 hour only. Yeah.
oh, okay, okay. So I think okay, and the next, yeah, on the Saturday we can discuss the. Mm. Yeah, that won't be that much mathematics. We can just discuss the how the hardware people make hardwares actually. That's it. Okay. Yeah, I'm
Also,
not sure if you,
a
yeah.
small, yeah, a small feedback here. When the when the resource person changes, no, sometimes there is a overlap of the content that has been delivered. So is it possible if they can see the recording of the previous session so that overlapping of topics or explanation of certain topics can be like yesterday morning what we had, there was an overlap with today certain
Yes, ma'am.
aspects.
Actually, I realized what you are saying. Even I have also observed. So we will be careful about this.
Yeah.
So we also want no overlaps between the topics. So like once a topic has been covered, we do not want it to get covered again, right? Because like new topics should be introduced.
So I
So
think
we will
this
Yeah.
be taking
recording will
care of
help.
that.
The recording may help also. If you share the recording with the next speaker.
Actually, we have scheduled topics for each of the volunteers. So even we
Oh,
don't even have to, yeah, we have already assigned the predefined the topics for each volunteers of what they are going to teach. So therefore,
okay.
we do not even need to check recordings.
Oh, okay, okay.
So we just need to follow it a bit more carefully. That's it. Because this is
Okay.
the first time everyone is doing. So that's why it may be a bit problematic. But yeah,
Yeah,
we will be able to like
yeah,
recover from that.
yeah. No issues. No issues. Thank you.
Thank you.
And
Yeah.
I think one comments about this maybe for yeah, maybe yesterday there was also another session, but I agree that maybe there could be some overlapping, but sometimes it happens to who is delivering the session. It for the first few minutes, 5 or 10 minutes, it sometimes to get the flow, to get the big dive onto the his contents actually sometimes he has to repeat the most repetitive things on a topics actually because those are the most fundamental things that must people say for to the audience, and after that he can make a platform and based on these platforms, he delivers his topic. So yeah, I agree. It shouldn't be repeat that much, but I think for first 5 or for the first few minutes, I think it is okay because we are talking on the same things actually. So just jumping on the things sometimes I'm not sure how it makes. But yeah, it should be careful, and for the who is delivering the talk, I think for the first few minutes is also we should be just have some patience that yeah, so that he can make a base, and upon that base he can deliver his particular sessions, actually his particular topics, his or her particular topics. Okay.
Yeah. Okay then, Sakib. So since so should we conclude? Then I will stop the recording.
Okay, good. uh, Thank you, and see you on Saturday.
Thank you, sir.
Bye. Have a good day. I mean, good night.
Thank you. Thank you.
Yeah, thank you.